this video is still about derivatives. Now, yesterday, sorry, the previous video, right? We came up with this equation, right, for derivatives, and we defined it in terms of x plus h. Okay, and so let's first talk about why this thing is called a derivative. Okay, so if you remember, the way we did it is from this function, right? We started with this function and we generalized, right? And we just said that this function is basically a function of x, which is x squared, right? So the main function over here is this guy. It's the function of x. Okay, you don't even need to remember that if it is a x squared, you don't really care. Okay, you've generalized it. So this over here, what you got is another function. Okay, so your original function was f of x, and you got another function from f of x, which is why you would call this guy a derivative function of f of x. Okay, so that's why we would in short form call this thing as a derivative. Now we could code that. Let's actually code it. So if I wanted to code it, I would say something like derivative, and I need to give it x and h, right? And then the way I would compute it would be x plus h minus the function of x and divide everything by h. Okay, so this is how I would compute derivative in a computer. Okay, so by writing this function. Okay, now here's something interesting. Now let's actually look at what the derivative will tell us. Okay, remember this graph every time I say derivative. Okay, this graph, because this graph is where we started, where we derived our derivative. So this was the graph, right? Something like this, and then we considered something like this was x, and then that must mean this is x plus h. So this is function of x, and this is function of x plus h. Okay, and our entire idea was this h over here, we wanted to reduce it and make it 0. Okay, so then that's how we got derivative function. I'll call it a derivative function is limit as h tends to 0 the function of x plus h minus the function of x divided by really x plus h minus x. That would result in a limit h tends to 0 function of x plus h minus the function of x divided by h. Okay, that is the derivative function. Okay, now let's look at a simple case. Okay, for a simple case, the way we started this derivation, right, was we use something like this. Okay, we're looking at actual values instead. So we looked at 1 and a 2. We're doing for y is equals to x squared, and this is a 1 and this becomes a 4. Okay, so over here, if I wanted to compute that derivative function, yeah, let's just say derivative. If I wanted to compute that derivative, then that is basically change in y with respect to change in x. Okay, that was the derivative. And that is 4. So change in y is basically this guy, f of x plus h minus f of x divided by change in x is basically f x plus h minus x, which is the function of 1 plus 1 minus the function of 1 divided by h, which is the function of 2 minus function of 1 divided by h. You know that h is just 1. Function of 2 is 4 minus 1 by 1, which will give you a 3. Now look at this. This number 3 is very, very interesting to us. see, we just calculated the derivative when your x, so here, let me write that down. When your x is a 1 and your h is a 1, okay? We calculated the derivative and it gives us a 3. What this 3 is trying to say is very, very interesting. So over here, whenever we talk about this, we'll always look at the graph. So look at this graph. Over here in h, right, h is a 1. So I move 1 unit to the right. What is happening to my y? Okay, my y is increasing by 3. That's what that 3 is really for. So that 3 tells me that if I go 1 unit to the right in the x direction, then I go 3 units up in the y direction. Okay, so that means look at, now let's think of that as our knob example. If I increase x by 1, then my y knob will increase by a 3. Okay, I increase my x, my y will increase. Okay, this also works in the left side, which means if I decrease my x, my y will also decrease. Remember this idea of increasing and decreasing, right? So y and x, right? If I increase my x, my y would also increase. If I decrease my x, my y will also decrease, which means that I am talking about directly proportional. I am talking about y and x being directly proportional when I compute the derivative for x is a 1 and h is a 1. Okay, so from this point, when my x is a 1, if I want to increase my y value, I should increase my x value. Okay, if I want to decrease my y value, then I should also decrease my x value. Cool, right? Okay, so that means when you have a number like this, a 3, a positive number, when your derivative is a positive number, that means what you should be doing is you should be increasing your x value if you want to increase your y value, or if you want to decrease your y value, you should decrease your x value. Okay, cool. So that's what a positive derivative turns out to be. Okay, so derivative being positive means directly proportional. Just means that you increase x, you increase y, you decrease x, you decrease y. Now let's look at another case for the derivative being inversely proportional. Okay, let's look at another graph. Actually, let's look at the same graph and I will show you how interesting this is. So if we look at the same graph, so this is x, negative x, this is x, this is y. Okay, this was the case for my x 1 and 2. Is that what we took? Yeah. What if I plug in my x as negative 1 and negative 2? What happens to my y value is you'll see something like this. Okay, let me make a better graph. You will still see your y would be a 2 and a 1 and a 4. Okay, so let me actually show that to you. Y is basically x squared, right? So my x and a y. If my x is a negative 1 and a negative 2, my y would be 1 and a 4, because negative 1 square is a 1, 2, negative 2 square is again 4. Okay, nice. So if I wanted to calculate the derivative, what would I get? Change in y by change in x when your x is, what is my x? I started looking at my x. Okay, so forget about this section of the graph, just look at this section of the graph. My x, I say, is a negative 1, and this h over here, my h over here is also a negative 1. So in this case, when my x is a negative 1 and my h is a negative 1, right? What is happening over here? What is my change in y? Change in y is basically 4 minus 1. What is my change in x? So I go to -2 from a -1. So that is 4 minus 1 minus 2 plus 1. That is a -1. So you get 3, -1. So that is a -3. Look at this. So when your derivative is a negative, it turns out that what that means is if you move, okay, if you move to the left direction, so look at what is happening over here, okay? Over here, if I move in the left direction, then my y is increasing, okay? So the negative derivative means that if I move in the left direction, which is if I decrease my y value, my x value, my y value will increase, okay? If I increase my x value, my y value would decrease. This is the idea of something being inversely proportional. So that means that when my derivative is a negative number, my x and y are inversely proportional, okay? So look, we know how to calculate a derivative. We have that function, right? And when that number that we calculate happens to be a positive number, then we know that x and y is directly proportional, okay? X and y is directly proportional. If that number that we calculate is a negative number, we know that it is inversely proportional. Now let's look at a case where your derivative would be 0, okay? What does that mean? So let's look at the same graph again. Y is equals to x squared. We'll still be using this example. So this graph will look like this. When your x is a 0, your y is a 0 over here, right? Right. So let's look at that. So your derivative is a limit as h tends to 0, function of x plus h minus the function of x divided by h, limit as h tends to 0. Now this is the first time we are literally using that formula to calculate something. What is your f of x plus h? It's basically x plus h whole square minus this is x squared divided by h, limit as h tends to 0, a squared plus 2ab plus b squared minus b squared by h, which is limit as h tends to 0. What the hell? So x square goes away, you get 2xh plus h squared divided by h. You can take that h as a common, you get 2x plus h, and h goes away, right? And limit as h tends to 0, 2x plus h, and your h is a 0, so you could plug it a 0 and you get a 2x, okay? And you're saying that your x is a 0, so your derivative should be 2 times 0, which is a 0. Wow. Okay, so at this point x is a 0, your derivative also happens to be a 0, okay? So at this point your derivative is a 0. What does that tell you? That tells you that no matter in which direction you go, you can go in the right direction, so over here in the right direction, or in the left direction, your y will no longer it's no longer decreasing, it's only increasing, okay? If you go to the, that means in our knob example, if you move to the right, if you increase your x value, your y value will increase. If you decrease your x value, your y value will still increase. So that's what a derivative being 0 means. So derivative being 0 means that x, no matter what you do to your x, y will increase, okay? So we have three things now of a derivative: positive, negative, and a zero. So positive just means that you are directly proportional. Negative means you are inversely proportional. And zero means that no matter what you do, no matter if you go left or right, you will just increase your y. So that means that you are at a point where your y is the minimum value. So this means that this is a minimum value for y. Okay, no matter what you do, in the left or right, you can increase your x in left, or you can do it in the opposite direction. Your y will always increase. So the zero case is your y is at a minimum value. Good. So this is what we needed to know. Okay, so right now we have a method with which we could calculate a number for a function, and that number will tell you what will happen when you would turn your x knob. Okay, what will happen to the y value when you turn your x knob. Cool. So all of this and all that we wanted to know was something being directly proportional or inversely proportional. Okay, and this is going to help a lot when we start literally coding our neural networks.